Good afternoon, guys. So we again here continue my discussion on strip method. So this time I'll be discussing the situation where one of the edges is unsupported and that is the long edge unsupported. For this particular beam panel, or sorry, slab panel, take note of the distribution of the load in the two strips. No? So the division of the strip is simply composed of a strong band. We call it a strong band, which acts actually as an edge beam support the and the width of this edge beam is dictated by a factor beta, which is chosen arbitrarily uh, within the limit of reinforcement. Okay. So the reinforcement limits for maximum and minimum both on slab in the beam. Okay, reinforcement ratios will dictate the value of your beta. So we want to keep it as low as possible to ensure, of course, a ductile behavior in case we are considering a behavior or failure modes beyond elastic. And if we are going to look into the distribution here, if this direction is assumed to be negative K2, it means that the loading here or the load distribution here simply is directed on the opposite direction. Okay, so if this is minus K2, then an additional load in this direction will be added, no, to the load W. Take note that 1 plus K2 minus K2 will simply be equivalent to W. Okay, so this will cancel out. And in this particular panel, no, so again, K1 plus 1 minus K1 will actually be equivalent to W because this will again cancel out. So in this particular uh, parameter, this will tell us if this is directed upward. No? So the load is directed upward, means this serves as your spring support. Okay? It's like a spring support that is uh, acting like an edge beam support code standards. So I normally use these strong ones where I need some additional beam within the panel, but I can uh, eventually add up to the configuration since the original model was not needed. So I use the concept of strong band in these particular cases. So for your uh, X direction strip AA and BB, so the loading diagram are here, 1 plus K2, so in this direction, and 1 minus K1 in this direction. Okay, so take note that this is directed downwards. So for the CC strip, you will notice the part here wherein minus K2W acts as a spring, which is actually a load directed vertically upwards. And this is K1 minus W in this regard. Then K1 can be chosen directly uh, using the formula below. Um, we can assume a distribution of K1 based on the previous lessons that I have given you. No? So arbitrarily chosen for us to be able to solve, okay, this equilibrium equation and definitely obtain a value for k. So here your MYS, okay, which is basically dictated by uh, this value here, considering strip CC, so this is your MYS, may be uh, assumed, okay, may be assumed for us to be able to get the value of k. Similarly, your beta can be assumed, okay, the same time as k1 can also be assumed. So knowing all the parameters here, including MYS, which is assumed on the basis of reinforcement limitations, then K2 cannot be solved. Okay, so your K2 here is very significant because your design for the strong band will be based on K2. So your W load will actually be greater uh, than 100% in this case. So for slabs with unsupported edges on the short direction, so we are now referring here on the short direction, the principle is the same, okay? But of course, since your strip model is basically more complicated than the first one here, then you have to take into account several sections AA on the longitudinal strip, BB, CC, and BD on the transverse strip. Okay, so for your load diagram on uh, strip AA, so definitely we have here this full load W and a minus KW spring support edge beam or edge, yes, edge beam support, which is again a strong band similar to the strong band that I discussed to you on the unsupported long edges. So it's a minus kW uh, value, and the moment diagram for this simply is negative moment here, okay, that will give you a more or less a value using a cantilever uh, uh, formula, and then suddenly reducing to a zero value moment to tension side, because this is a spring supported roof. It's not capable of withstanding any moment at this point. So taking moments at left, okay, so this is now my formula. So your WB squared all over 32, okay, which is basically this one, plus mxs, so the wb squared over 32 is actually this one here, because this is b over 4, okay? 4 squared 16 over 2, so we have w b over 4 squared over 2, so this is wb squared over 2, and then plus mxs minus this one here, kwb over 4 times a minus b over a. So we are taking moments into left support, so the distance from here up to here is the moment arm. Okay, so this is kwb over 4, just like the kw uh, is b over 4, okay, times the moment arm, which is a minus b over 4 over 2 is b over. So this is now the summation of moment. And solving for the k value here, assuming again that mxs is determined on the basis of reinforcement limits, okay, and everything is just known, you can solve for your k value, okay? So that's the way how to solve for your k value that will dictate ever spring support or spring constant you ought to use in your diagram. You can plug this directly on a software, no? If you want to more or less make it much comprehensive and get into the variations of the moment diagram. Okay, if we solve for, these are actually mx. Okay, if we solve for the mx or the maximum moment or span moment mxf, we can simply uh, this one here, this is the mx, okay, we can simply make use of this formula, and I ought uh, to to give you the process of verifying this when you are at free time. It's equivalent to kwb squared over 32, and this is one uh, a positive moment that will give me the reinforcement needed for my design. So for the moment in the x direction edge strip are simply half the values above. Consider the y direction strips, strip CC, EB, and DB. These are the strip CC, DB, and BB. So these are the loading diagrams. So all we need to get is moment negative and moment positive in terms of MYS and MYF, which are this and this. Okay, strip CC. Remember that the cantilever moment is simply E over 4 W B over 4, sorry, B over 2 squared over, that's why this becomes equivalent to WB squared. Okay, so this is strip CC here. Okay, so this strip CC has a B over 4, I think this is It's strip CC. P over 2. This is fully loaded, rather, P over 2. So for a fully loaded span, so full load, your X is P over 2. So for adopting a 2 is to 1 kasi ratio for M positive or M negative over M positive. So all we need to know is that for 2-1 ratio, my moment negative and moment positive will simply be distributed 2/3 and 1/3, okay, of the whole moment. Okay, so this is 1, 2. Okay, so 2/3 of this is 1 over 12 and 1/3 of 8 is 1 over 24. So this is simply the same as a fixed, okay, moment diagram like this, where this is W B squared over 12 and this is W B squared. Okay, it's just the same. So for strip BB, use 1/8 values of strip CC since we noticed that in this particular case there's no loading at the mid strip here, and this is B over 4 W over 2. Okay, so B over 4 is simply 1 over 8. Okay, so we're talking here of B over 2 uh, converted to a B over 4. So simply this is a 1. If we square this, we're talking of 2 times 2 is 4. Okay, so B over 2 squared is 4, or 16 over 4 is 4. So the ratio here is 1/4. And then if we talk of W, we have a W versus a W over 2. Then 2 times 1/4, 1/2 times 1/4 is 1/8. So the factor 1/8 was used as strip DB. And for strip DD, we use the values of strip CC, we simply multiply it by a 1 plus k, which is a conservative S. See, so those are the moments. By selecting a proper value of MXS, if A over B is large, then MXS approaches a prop cantilever plus 5. If A and B is approximately equal to 1 squared, then MXS 1/2 MXS of the cantilever. So what does this mean? It simply means that when I have here a cantilever beam approaching to a prop B, the value in between will simply be a range, considering here a zero support and a full prop support, and this becomes now a split support. And of course your MX1 S1 here is greater than MXS2 and MXS3. So if A over B is equal to 1, then you have a prop cantilever in case. So once MXS is selected, okay, again, this is selected on the basis of reinforcement limits, okay, K is computed from this formula. So K is computed from formula above, okay, so this is your formula K here, and your value for X, which is the point where the maximum moment is given by this formula. So when K is computed, X is 1 over K B over 4. So this is now the value of X that will give you the point of maximum moment. Okay, so this is the point we're in. So for you to be able to locate your reinforcement correctly, then you need to solve for these x. Since your moment diagram is a little bit awkward in this case here. Take a look at this moment diagram. So you have to favor more positive reinforcement very near the side of the support. So you need to solve for the value. Okay? So that's it for uh, slabs with unsupported edges. See you in the next video to discuss to you slab reports. Thank you.